Recursion is a programming method that's completely different from what you've seen so far. What you've learned so far is what we call iterative programming. Iterative programming is a programming technique that uses instruction loops that repeat themselves, that evaluates to nothing, and that uses what we call side effects in order to return values, meaning they use variables. Let's use your function string length as an example. I hope you've done it. That takes a variable, initiates it to 0, and does a loop that at each iteration, note iteration, iterative programming and all, will increase your variable by 1. So it's using an external variable in order to return its result. Its result, it doesn't really return one. It's stored within a variable. Iterative programming is exactly like this. The function string length is a canonical example. Recursive programming is a little different. You have to picture it just like Russian dolls. We'll have functions calling themselves, and then they call themselves again, and call themselves again, and call themselves again, etc. up to a certain point. We will use mechanisms to return results. In order to understand this, you must first understand the principles of a pile. And by pile, I mean the stack. It's a programmed reserved region of memory that will fill up as we call functions. That's pretty much empty at the beginning of the program. For example, let's use a simple program. At the very beginning, the stack is empty. When we start the program, the main is called. So the function main will be put on the stack. We could also say that it's pushed onto the stack. And then, somewhere in your code, the main will call your function putString. Therefore, we call function putString that will also be added to the stack. And somewhere in function putString's code, function putCharacter will also be called and therefore will also be added to the stack. Function putCharacter will then call write, which will also be added onto the stack, etc., etc. Basically, every time we call a function, this function will be pushed onto the stack. It will evaluate itself, and at some point, when we're done with our function, we'll return to our previous function. Our function that was on top of the stack will be removed from the stack. We can also say that it's popped from the stack. So our function will be gone and be replaced by the previous one. In our example, we remove write and function putCharacter will remain, and our execution will come back to function putCharacter. We'll keep going and remove function putCharacter and go back to function putString, then go back to the main, etc. As I said before, it's like Russian dolls. Functions pile up on top of each other or within one another, and that's the principle we use for recursive functions. And recursive function is a function that calls itself. And that pushes itself on the stack on top of itself. In principle, it's not that complicated. However, we'll do this until we reach two possible outcomes. Either you have a function that's okay with always just calling itself, in which case every time it'll finish its action, we'll re-push another instance of our function onto the stack. And as you can imagine, if we don't stop, the stack will grow and grow and grow till it goes kaboom. The program will crash because your system will inform it that it's gone over the stack's capacity, the one allocated to it. And as you can imagine, that wasn't such a brilliant idea. The second possible output in this kind of situation, and that's what we normally should do when we use recursion properly, is to get to a point in our execution where there's a stopping condition and tell ourselves at some point in our function, let's call it function, which is a function that calls itself, that there's a condition that states that if a criteria is met, then we can stop calling it and return it instead. It's as if you said, enough, I'm stopping now, I'm going to keep on using recursion, otherwise the stack will break down. It's the same principle as a stopping condition in a loop. Actually, it's exactly the same principle, except that it's being implemented differently. So when we reach our stopping condition, we stop piling our functions onto the stack. We pop the functions, and we go down the stack to return to our initial state. Now, let's check out a small mathematical example on Vim. I know everybody's not a fan of math, but in case the example is appropriate, let's talk about factorial functions. For those of you who haven't done math in a while, or those that have a selective memory, a factorial function can be written as follows. Factorial 5 equals 5 times 4 times 3 times 2 times 1. X equals multiplication. Same goes for 6. 6 times 5 times 4 times 3 times 2 times 1. I'm sure you get it. I can show you with another couple of factorial 4. 4 times 3 times 2 times 1. Factorial 3. 3 times 2 times 1. And if you think about it, we could say that factorial 5 is like doing 5 times 4. Or factorial 4 is the same as 3 factorial multiplied by 4. It could go on like this forever until I reach factorial 1. Simple fact, factorial 1 is 1. Notice the resemblance with recursion. We can see that 5 factorial equals 5 times 4 factorial, 4 factorial equals 4 times 3 factorial, all the way to 1 factorial equals 1, which is kind of a stopping condition. Just in case it's not clear enough yet, let's say that for n being greater than 0, n factorial equals n times bracket n minus 1, close bracket, times n, open bracket, n minus 2, close bracket, times, and you carry on, etc. Until 3 times 2 times 1. Based on this example, we could say that factorial n equals n times factorial n to the minus 1, n minus 1. Easy peasy, right? So factorial n minus 1 is equal to n minus 1 times factorial n minus 2. Etc., etc. Until we reach 1, which will end our recursion. That was a form of recursion. Written in math, granted, but still. I'm going to show you recursion in code. Not in C though, that'd be too easy, but in pseudocode. We can write that the function fact n is equal to n times fact n minus 1. Therefore, it's a recursive function and it needs a stopping condition. As you know, the factorial for 1 is equal to 1. From this example, you should be able to build a recursion with a stopping condition that will execute without making your program explode. At least I hope so. So, in order to calculate the factorial n, we need to calculate that of n minus 1, etc. It looks a bit like a loop, and it could be written as such. You'll have to do it anyway. Let's stop for now and see you in the next video for more examples in real C code.